Hi, my name is Shakufe Hedayati, and I will be presenting about our recent work named Memory for Latent Representations. This is a pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. This work has been done by the collaboration of Weibel Lab, including Ryan O'Donnell and Dr. Brad Weibel. It is really hard to separate the working memory from long-term memory. And in classical works on this matter, it's been shown that these two mechanisms are highly interconnected. However, it is not clear exactly how working memory builds representations from the visual knowledge, and that's what we're trying to address in this work. We will show how working memory stores familiar items, how it stores novel information, and how it can store multiple codes of an item. And what do I mean by multiple codes? Well, in a case of a red circle, the memory can store it as a categorical information or a noisy version of its visual information. The MLR that we're proposing here is the model of working memory visual knowledge that builds working memory representations from the visual knowledge. This model has two important elements: the binding pool, which operates as the working memory part, and a modified variational autoencoder, or the MVAE, a fully connected neural network that can represent visual patterns. The MVAE indicates the visual knowledge in this model, and I'll be explaining each of these elements in more details. First, what's the binding pool? The binding pool mechanism is very similar to holographic representations, which has holistic distributed representations across a fixed large number of neurons. There are works by Plate and Kavanagh about holographic models of memory. The binding pool that we used was borrowed from Swan and Weibel in 2014. In that work, their model had a type layer that represents high-level visual features such as color, orientation, tokens that are to individuate objects and helps to keep track of multiple items encoded in memory, and a binding pool, a domain general memory system that encodes the information in a shared resource pool. For a given item, features are bound to a token using fixed weights, and the information is encoded in the self-excitatory neurons in the binding pool. Similar to the binding pool model proposed by Swan and Weibel, the MLR model has tokens and the binding pool layer, but instead of a type layer, it has a VAE, a neural network that learns to represent complex patterns as opposed to simple features like color and orientation. VAE was first introduced by Kingma and Welling. It consists of an encoder, a latent space that has the most compressed form of representation, and a decoder that outputs the reconstructed image. The VAE learns, using gradient descent, to compress the information without losing much of the visual details. In this example, the input has 784 pixels, or dimensions, and the model learns to represent this information in the latent space with only 2 neurons. Here you can see a two-dimensional space of a VAE that's been trained on thousands of handwritten digits from 0 to 9. Each location in this surface represents a specific shape. For example, this 8 could be the closest representation of the input A8 in this model that corresponds to this level of activation of neuron 1 and neuron 2. I should note that although the latent space is great in representing the items that's been trained on, it cannot really represent novel information. If I show a letter B to this model, that's only seen digits, it will probably reconstruct a digit similar to letter B, like an 8. As I explained the VAE, you might ask yourself, what were the reasons we used VAE to represent visual knowledge in our model? Well, one reason was that the VAE resembles the hierarchical visual ventral stream. So L1, L2, and the latent space correspond to V1, V4, and IT cortex. And we can think of L4 and L5 as feedback connections going back from IT to V1. Another reason to use the VAE is that we could test the working memory performance when information is encoded from any of these layers here. We'll later show, for example, that familiar shapes could be better encoded and retrieved if they are encoded from the latent space. And novel shapes, on the other hand, could be better stored and retrieved if they are encoded from the early layers of the VAE. One modification that we did to the VAE was splitting the latent space into shape and color maps using separate objective functions. We used MNEST datasets that had 70,000 handwritten digits and Fashion MNEST consisting of 70,000 articles of clothing. We colored them by 10 prototype colors with some minor variations. By keeping the shape and color representations distinct, we were able to reconstruct both shape and color, only color, or only shape of the stimuli. We also added and trained a skip connection going from L1 to L5 to later retrieve novel information. Now that we learned about the VAE and the binding pool, I can explain the series of simulations we performed on MLR, such as encoding and retrieving a familiar and a novel shape, encoding multiple codes of an item, encoding multiple items in memory, and binding colors to shapes. Let's start with the first one, which is encoding and retrieving a familiar shape. To encode the information from L1 and L2, these images are shown to the model one at a time, such that the binding pool stores only one image at a time. Activation from L1 are projected to the binding pool using random and normally distributed fixed weights. Then they are projected back to the L1 using transpose matrix multiplication, and then they're reconstructed through the VAE. Similarly, to store information from L2, activations from L2 are projected to the binding pool, then they're projected back to L2, and they're reconstructed through the VAE. We can also see the memory encoding for shape and color maps. Again, in this case, images are shown one at a time. The activations of the shape map are projected to the binding pool, then they're projected back to the shape map, and then they're reconstructed. Similarly, for the color, we could reconstruct only the color of images. And using the same method, we could also reconstruct both shape and color of the original stimuli. To examine the quality of representations being stored from different levels of the VAE, we trained classifiers on shape and color maps. For example, SVM-C maps the color activations to color labels, and SVM-S maps the shape activations to the shape labels. And this is how memory retrievals look like for L1, L2, and shape and color maps. We can see the quality of the retrieved images are better when information is encoded from higher levels of the visual system, such as the latent space here. This is also evident in classifiers' accuracy that show a higher accuracy for the latent space compared to L1 and L2. Now let's see how our model encode and retrieve a novel shape. For novel shapes, we use the handwritten colored Bengali characters. The model has not been trained on these characters at all. In this case, each stimulus is stored in the binding pool from L1, and then it is projected back to L1, and it is reconstructed through the skip connection instead of going through the latent space to reconstruct the novel information. The MLR model can also store multiple codes of an item. For example, a red 9 has a shape and color representations in the shape and color maps. We could estimate the categorical information of these representations using the pre-trained classifiers, here red and 9, and store them in the binding pool along with the visual information. So far, we showed how one item is stored in the binding pool, but using the tokens, we can also store multiple items in memory. This is an example of multiple items being encoded in the binding pool, with each token being associated with one of the items. So, consistent with many previous behavioral experiments, the MLR showed interference when more items are stored. We can also see from the classifier's accuracy that the rate of interference is higher for visual information than for the categorical information. In other words, visual information are more subject to interference as the set size increases. And in our last simulation, we showed the binding of colors to shapes. Let's imagine that a color 2 is stored in the binding pool. In the next step, another item here from the same category is stored in the binding pool associated with the token 2. Then we probe the VAE with the shape of the first item to retrieve its token. Finally, that token can be used to retrieve the whole item. We could show that accuracy of finding the correct token was 87% when digits were from different categories, and it was 70% when digits were from the same category. In conclusion, MLR model provided a mechanistic linkage between long-term memory and working memory. We showed that familiar items could be encoded efficiently in memory by taking an advantage of compressing the information without losing much details and categorization, whereas novel information lack both compression and categorization. Finally, we are hopeful that our model sheds light on the previous descriptive models like Atkinson and Schifrin, and also Baddeley and Hitch, in which they discussed the important role of long-term memory in short-term memory and working memory performance. Thank you very much for your attention, and I'd be happy to answer your questions.